Example 2.1, 3 charges. 3 fixed point charges. Q1 equals positive 1.50 microcoulomb. Q2 equals positive 2.50 microcoulomb. And Q3 equals negative 3.50 microcoulomb. Charge Q1 is located at 0, A. So this is charge Q1 at a distance A along the y-axis from the origin. Q2 is located at 0, 0. So this is Q2 at the origin. And Q3 is located at B, 0. So Q3 is along the x-axis, a distance B from the origin, where A equals 8 meter and B equals 6 meter. What electric field do these 3 charges produced at point P equals B, A? So this is my point P at B, A. And we need to find what is the electric field produced by these 3 charges at point P. So before we solve for electric field, let us first find what are the distance of these charges from point P. Let the distance between charge Q1 and point P be R1, and R1 is equal to B, as you can see from the figure. So we can write R1 to be equal to 6 meter. Then the distance of charge 3 with point P will be R3, and R3 is equal to A, which is 8 meter. Distance of charge 2 from point P will be R2, and R2 you can find by using Pythagorean theorem. So I will write R2 to be equal to square root A squared plus B squared, which will be equal to square root 8 squared plus 6 squared, and that gives me R2 to be equal to 10 meter. After we find the distances, now we are going to show the direction of electric field at point P. Now charge Q1 is a positive charge, and we know electric field due to a positive charge go away from the charge. So electric field at point P because of charge Q1 will point away from it towards right, and we will call this E1. Then charge Q2 is also positive, so electric field due to charge Q2 will also point away from Q2 along the line joining charge Q2 and point P. So this is electric field due to charge Q2. I will call this E2. Q3 is a negative charge, and electric field lines points towards negative charge. So electric field at point P because of Q3 will be along the line joining Q3 and point P, pointing towards the charge Q3. I will call this electric field as E3. So these are the electric field at point P. Over here, E1 and E3 lie along X and Y axis respectively, but E2 neither lies on the X axis nor on the Y axis. So we need to split E2 into its component. One component that will go along the Y axis, which we will call as E2Y, and the other component that goes along the X axis, which we call as E2X. So this is the graphical description of electric field values at point P. Now we are going to calculate its magnitude. In order to calculate the magnitude of the resultant E, we will first find what is magnitude of E1, E2 and E3. So we can write E1 to be equal to KQ1 over R1 squared. That will be equal to K is 9 times 10 to the power 9. Q1 is 1.50 microcoulomb. So 1.50 times 10 to the power negative 6. The distance R1 is 6. So 6 squared. That gives me the value of electric field E1 to be equal to 375 Newton per coulomb. Then we calculate the value of E2. E2 will be equal to K Q2 over R2 squared. So K is 9 times 10 to the power 9. Q2 is 2.5 microcoulomb. So 2.5 times 10 to the power negative 6. Distance between point P and Q2 is R2, which is 10. So 10 squared. That gives me E2 as 225 Newton per coulomb. Now E2 we are splitting into components, and we need to find the values of this component. So let the x component of E2 makes an angle theta with the resultant. And this angle theta is the same as the angle theta over here. Theta we can calculate by using any of the trigonometric ratio. I will use tan inverse to find this theta, since tan is associated with opposite side and adjacent side, and we have both of these values. So I get this theta equals tan inverse y over x, where y is the opposite side, x is the adjacent side. So we get tan inverse, y value is a, which is 8, x value is b, which is 6, and that gives me the theta to be 53.1 degree. This is the angle E2 makes with the x-axis, and by using this angle, I'm going to calculate its component. So we write E2x to be equal to E2 cosine theta. Cosine because this is the component that is attached to angle theta, therefore it is associated with cosine. So we get 225 cosine of the angle 53.1. That gives you the x component of E2 as 135 Newton per coulomb. E2y will be equal to E2 sine theta. That gives you 225 sine of the angle 53.1. And when you solve this, you get E2y as 179.9 Newton per coulomb. After this, we find E3. E3 you can calculate as K Q3 over R3 squared. That will be equal to 9 times 10 to the power 9. Q3 is negative 3.50 microcoulomb. But when you are finding electric field, we do not put that negative sign, as the direction of electric field we take from the vectors here and not from the sign of the charge. So I will just take the magnitude, which is 3.5 micro, so 10 to the power negative 6 over R3, which is distance A, so 8 squared. That will give me E3 to be equal to 492.2 Newton per coulomb. Once I found the values of E1, E2 and E3, I'm going to find the net electric field along the x-axis and the net electric field along the y-axis before we calculate the resultant. So along x-axis, you have two components of electric field. One is E1 and the other one is E2x. Both of them are going towards the right, so we take them both as positive. So I will write E net along the x-axis to be equal to E1 plus E2x. E1 is 375 and E2x is 135. And when you add them, you get the net electric field along x-axis to be equal to 510 Newton per coulomb. We do the same thing along y-axis. We write E net along y. Now along y, there are two components of electric field. One is E2y, which is going up, so we will take this positive. And then you have E3, which is going down, so we will take this negative. So you get E2y minus E3. E2y is 179.9 minus E3 is 492.2. And when you solve this, you get the net electric field along y-axis to be equal to negative 312.3 Newton per coulomb. After we find the x and y component of electric field, now I will find the resultant magnitude. The resultant electric field can be found by using Pythagorean theorem. I get E equals square root E x squared plus E y squared. And this x and y component are the component of the net electric field here. So let's substitute square root 510 squared plus negative 312.3 squared. If you're putting the negative sign, make sure you put it inside the bracket while you square it and not keep it outside. So when you solve this, you get the magnitude of electric field to be equal to 598 Newton per Coulomb. So this is the magnitude of net electric field at point P. We can find direction of electric field by using tan theta, but instead of calling our angle theta, I will call it alpha, because theta we already used here to find component of E2. So I will write alpha, which is the angle the resultant make, to be equal to tan inverse of EY over EX. Again, X and Y component here are for the resultant. So you get tan inverse. Y component is negative 312.3. X component is 510. And when you solve this, you get alpha to be equal to negative 31.48 degree. So this is the magnitude and direction of the resultant electric field at point P because of these three charges.